Now go ahead.
Yeah, go ahead.
So thanks, Francesco, for coming and joining us this week.
Thanks to you for having me and for coming to see this talk. I hope it's you will find it worth. Okay. All right. So yeah, let me just go back a second. It's just going by itself.
Yeah, you can pause it.
Okay.
Yeah.
Okay. So so discussing with Anna before coming, we decided that I would talk about some results that we have about quantum measurements, in particular POVMs, about sharpness and instruments with respect to the incompatibility problem. And I will show you that there are these two problems in the literature, and that a possible way to solve the problems is to approach these two topics from the viewpoint of resource theory, in the very practical sense that you want to understand these two concepts of sharpness and incompatibility in terms of transformations, right? And the possibility of simulating stuff with resources and so on. And this somehow forces you to leave a little bit of the mathematical formalism behind and go straight to the point, the core of the problem. So that's why probably this resource theoretic approach was useful. Okay, so these are three references about these things. Okay, just to set up the notation.
You can use the pointer to flip the slides.
Okay, all right. So just to set the notation, I will be working only with finite discrete sets. Everything is finite. So a POVM, positive operator values measure, what it is a family of positive semi-definite operators, PX, that sum up to identity. Okay? And these are used to compute the expected probability of an outcome in a measurement. So given a measurement, you can say, okay, this is going to be, the outcome is going to be some random variable, some classical random variable, and the formalism of POVM allows you to compute the expected probability of each state of this outcome random variable. If you want to do more with quantum measurements, for example, if you want to compose quantum measurements one after the other, so if you want to have a notion of a series of measurements or a sequence of measurements, then you need something more. You need to have a rule or a recipe that allows you to compute the state after the measurement. So this is not given to you by POVM. You need something more, a kind of more detailed description of what's going on, and this is given by the notion of an instrument. So now, an instrument is a family of, now these are maps, in particular completely positive linear maps from some input quantum system to some output quantum system. And now this summation to identity is replaced by the fact that the average map in particular is trace preserving, right? Which means that, in average, if you care only about an average evolution, this will happen with probability 1. It's deterministic, right? And again, the interpretation is that, again, you can compute the expected probability of each outcome in this way, but you have more. You have the corresponding post-measurement state. So given that some outcome X is observed, and that your measurement was described by this instrument, this is the state of the system after the measurement has been performed and the outcome has been recorded. And then another notation that I will use is this DAGA here. What is a DAGA of a linear map? It is just a trace dual. So you use linearity here of the map and you plug it into a trace, and this defines a trace dual. So like so-called like Heisenberg picture where you split the Krauss operators of your map. Okay, so let me start by presenting you the problems, and then let's see, because if there is time, maybe I can tell you about both solutions, but if we don't have time instead, maybe you will tell me which problem sounds more interesting to you, and I will focus only on that one. So the first problem is a problem with measurement sharpness. So first of all, what is a sharp POVM? So this is about POVMs. What is a sharp POVM? It's a POVM whose elements are all orthogonal projectors. So it is also called a PVM, right? Projection value measure. And it's sharp, why? Because orthogonal projections are pointed. Not to touch an angle here, it's sharp. So that's why it's sharp. Another reason maybe it's because sharp POVMs or PVM are like the paradigmatic model of a repeatable measurement. Following von Neumann book, for von Neumann, repeatability is a super important property that measurement have to be called measurement, right? And so repeatability means that you can repeat, even though here it's POVM, so there is no notion of instrument, but somehow, the von Neumann rulers, PX or PX. If you do this over and over and over again, you will keep getting the same output. So it's clear-cut measurement. One more reason to call it sharp.
So how do you refer to rank 1 POVMs?
Oh, here there is no particular, you can say non-degenerate observable.
You wouldn't call it sharp.
Yeah. If the operators are orthogonal,
Yes, but
it's sharp.
If it's rank 1 but not orthogonal.
It is not about sharpness. No. It doesn't play any particular role here. Rank.
When you say it's repeatable and then you do it over and over, you mean on the same system, right? Not that you get n systems and just do it.
No, in a sequence. So
And then you only get the same thing and scale it.
yes. So sharp measurements are nice in a sense because they satisfy these properties. And indeed, already in 2005, Paul Bush somehow thought of sharpness as a resource. It was antelitteram, of course, because there was not all this fuss about resource theories by then. But he imagines sharpness to be something that you can measure using some sharpness measures. Okay. And there is some recent work by other authors. The problem is that the attempt to construct a resource theory of sharpness have always been affected by some problems. Like at some point, you don't know how to transform sharpness. Some transformation works, some do not, and people have been left, wondering whether it is possible at all to understand sharpness from an operational viewpoint. Because what can you do? Okay, so a theory of sharpness should be a theory where objects are POVMs, and you want to transform POVMs into other POVMs. So what can you do on a POVM to get back another POVM? You can do, for example, a quantum preprocessing, right? So you can stick, before plugging your state into the POVM, you pre-process your state with some quantum channel. And so it means that your POVM gets transformed into dissolved for some CPTP linear map E. You have this E data, no? Because on the POVM you have the pre-dual path. Another thing that you can do with POVMs is instead to degrade them. So to take the classical output that you get from the POVM and transform it, shuffle it with some noise, stochastic noise, into some other outcome Y. This is classical post-processing because it acts only on the classical outcome. Or another thing that you can do with POVM is to convexly mix them. Okay? So you have another fixed POVM that you choose, and now you say, okay, I take my input POVM and I construct the convex mixture of these two objects. Or any compositions of the above, right? So these are the things that you can do with a POVM. But now there is a problem with processing sharpness with it, because essentially none of these operations is legal. So all of these operations can lead to an increase of sharpness in the sense that you can start from a POVM that is not sharp, so it's not a PVM, it's not made with projections, and yet after the processing you end up with a projected POVM. Okay, so for example, like quantum preprocessing, it's illegal. The example can be very, very easy because I can start from POVM, just a diagonal POVM like this. Okay, this is 0. And here I have 1, 0, 1/2, 1. Okay, and then I can take the channel E that does this. So essentially, it takes a 2 by 2 matrix, A, B, C, D, and gives me A 0, 0, 0, 0, 0, 0, 0, B. Okay, so if I apply the trace dual on this object, 0, 0, 1, 0, 0, 0, 0, I get the projector onto 0, and if I do the same on the other matrix, so create 1/2, 1, 0, I get 0, 0, 0. Okay. So I start from something that is not projection, because you have this eigenvalue 1/2. This is a trace preserving positive map. It's super simple, right? I just take the diagonal elements and. But when you do the trace dual, it does this thing. So it maps this into a projection. Right? So this is bad. Classical cross processing are bad too, because this is even easier to see, right? You can start from a POVM like this, right? And then your post-processing is just merging this outcome into this. So you end up with a projected POVM 0011. And then you saw also for convex mixtures, right? You're stuck because first of all, you have to tell me what is the maximally dull POVM before mixing the case, right? Because if you mix something that is sharp, of course you can increase sharpness, right? So somehow you're stuck. And indeed, I mean, people that have been trying to construct a resource theory of sharpness got stuck sooner or later in when constructing or trying to characterize a family, a class of sharpness non-increasing operations.
Why is sharpness not increasing? Something we are asking for.
Yeah, so if you want to imagine sharpness as a resource, okay, typically you want to start by defining a set of operations.
Okay.
So in this case, will be operations acting on POVMs, but operations that by construction do not increase sharpness. So typically, you don't want that you can start from something that is not sharp and end up with something that is sharp. Would be like in the theory of entanglement, saying, okay, I want to have an operational theory of entanglement, and I suddenly find out that my operations allow me to go from a non-maximal entangled state to a maximal entangled one. And then, this is a red flag. No. This cannot be a resource theory of entanglement. It should be something else, but definitely not. Maybe something else, but definitely not. So the same you want for sharpness, right? Okay, so this is the problem with sharpness, the first problem. And let's see, time permitting, I will tell you something about the solution. The second problem is about measurement incompatibility. Okay, incompatibility is good because without incompatibility, you wouldn't have quantum key distribution, you wouldn't violate Bell inequalities, you wouldn't have quantum speedup, so it's good. And then, how can we formalize the notion of incompatibility? There are many approaches, but I would say that there are three big families of approaches. One approach is by considering preparation uncertainty relations, like the Robertson inequality, that tells you that you cannot prepare a state that is that has sharp values for any observable that you want. Some observable are incompatible. So, for example, if you prepare a state that has a definite value for, I don't know, the spinning direction x, so will not have a definite value, cannot have a definite value of the spinning directions. This is preparation. You can also think about incompatibility in terms of measurement uncertainty relation, that when you want to measure a quantity, you're going to cause, definitely, depending on the accuracy with which you measure the quantity, you will cause an uncontrollable kick on another quantity that is not compatible with that one. Okay? But there is also another notion of incompatibility, which is the one that we consider here, which is more algebraic. Right? So it's a kind of mathematical condition that you can check whether two quantities are compatible or not. So what is clear in the literature is the notion of compatibility for POVMs. Okay, this is I would say now it's a widely accepted definition of compatible POVMs. So now you have a family of POVMs. Okay, I is the label of the POVM, and then within each POVM you have alpha x. So this family is compatible whenever there exists a mother POVM. So it is just one POVM with some outcome W, and then a conditional probability distribution that depend on the outcome of the mother and the label that tells you which POVM you want to measure or simulate, such that this relation holds for all x and for all i's. So it means that essentially the situation is the following. Well, this is the mathematical definition. So what does it mean? Operation. So if you say, okay, in my laboratory, I can only do compatible POVMs, what it means? Is it something that has to do with the cables in your laboratory? Yes. Because you can think that behind there is a bipartition going on, like the following one. So a family of POVM can actually be thought as a bipartite channel, where on one side you plug your quantum state, and on the other side you plug the program, the classical program that decides which POVM you want to measure. And then what it means that in your laboratory, you are not able to keep a state, to keep a quantum memory long enough to decide the program. So somehow it means that your laboratory is, as kind of weak, right? Because whenever you are given a quantum state, it is like a hot potato for you. You don't want to handle it for too long. You want to measure it quickly, and then it's dead. The quantum state is no more. You only have the mother outcome, and then you can post-process the mother outcome. Okay? So if you say in my laboratory I only have compatible POVM, it means that you are in a situation like this, and vice versa. A situation like this can only give rise to families of compatible POVM. Okay? So for POVMs, it's quite clear, and everyone would agree that this is the right notion to consider. The problem is when you go to the level of instruments. And now, unfortunately, in the literature, there are two schools of thought. Quite ironically, both of them created by Teiko. Excuse me, the pun, but they give you like incompatible views on incompatibility of instruments, right? Really, that they would not. So one school is to consider classical compatibility. So classical compatibility basically extends to instrument and the idea of compatibility for POVMs. So in that sense, it's classical, right? So I give you now a family of instruments. Again, I is the which instrument, and X is the outcome for all instruments. Right? So the family is classically compatible whenever there exists a mother instrument, okay? And then a conditional probability distribution that takes the outcome, the classical outcome of the mother, and stochastically post-process it into the outcome of the other instrument. Okay? So as a picture, you have this. So you see that it is exactly as the one for POVM. The only difference is that from the mother, you have a quantum system coming out, this D. But like causally, the causal structure is exactly as before. Okay? So a crucial thing is that classically compatible instruments, or like now you have bipartite channels basically, are necessarily no signaling from the classical program to be. Okay, so that's why some authors argue that this is the right notion to consider compatibility of instruments, because then you can join with the literature of no signaling boxes, and there is a deep structure there, so they're very happy to make a connection. However, there is another, yeah, it just looks bad, right? It looks bad. There is another approach to incompatibility, which comes from another intuition that you can have from the situation for POVM. So before for POVM, I told you that, okay, you take the outcome of the mother and you post-process it. But actually, because the outcome is classical, you can always imagine that you make many copies of it, you do a fan out of the outcome of the mother, and then you apply the post-processing on each of these copies, which are perfectly correlated. So you can say that the mother basically outputs at once, simultaneously, from the beginning, everything that is needed for the family of POVM. So then you just throw away what you don't need, and you take only the marginal for the outcome that you're interested in. So now this other notion for instrument starts from this intuition. So again, you say, okay, so now what is this notion of parallel compatibility? It's this. As I told you, the mother instrument should output everything simultaneously from the very beginning. Not only the classical outcomes, but also the quantum output. In a picture, it's like this. So now you have this mother instrument that outputs all the quantum outputs at once, and yeah, you can imagine that these are all the classical outcomes already. And then only at the end, when you know which instrument you want, you keep only the piece of information or the information that you like. This is so-called parallel compatibility. And people argue. So people write papers saying classical compatibility is better, is more fundamental, because we are doing the theory of non-signaling boxes, and that's the direction to go. But then people instead pushing, the idea of parallel compatibility, they say that this is the most natural, because they think it's the most natural, right? Yeah.
So in this setting, can you also think of what is the W as a tuple of x's,
Yes, yes,
and the mu is just selecting the
Yes,
coordinates?
yes, yes. You can always do that. And but so now the point is that these two descriptions are, in our opinion, too limited, both of them. Okay. And first of all, I will show you that they are incompatible. They really lead you to different conclusions, right? First of all,
You forsake us.
give me a synonym of incompatible in this case. They inequivalent, yes. They are logically inequivalent. Why? Because, well, we said that if your family of instruments are classically compatible, you cannot have signaling from here to here by construction. However, here you have signaling going here, and so the channel from A to BI can be different for a lot, the average channel. So parallel compatibility can signal, okay, and so it cannot imply always classical compatibility. But also the vice versa holds, right? Because parallel compatibility now has nothing to do with the no information without disturbance principle. In particular, non-disturbing instruments can never be compatible, because here you would violate no broadcasting, so you would be broadcasting perfect copies of your state. And I will show you kind of. So also classical compatibility does not imply parallel compatibility. So there are situations in which the two schools disagree, right? For example, take this silly example, I would say, okay? Two instruments. Neither one does anything whatsoever on your state. It just let the state go through, okay, and flips a coin. Okay, just not to be too trivial, I didn't put here 1/2, 1/2, because then you would say, but that's the same instrument. Actually, that's true. You can also put 1/2, 1/2. Just for the sake of notation. On one side, it flips an unbiased coin, the other side, it flips a biased coin, but still the state goes through. This thing, however simple it looks, of course it's classically compatible, but surprisingly to me, this is parallelly incompatible. And the reason is that the channel is identity channel. And so if you want that both instruments are output simultaneously by the mother should be able to do perfect broadcast, perfect clone. But okay. Another kind of silly example is this. So the POBN is the same. Okay, I give you a qubit state, you measure the computational basis, but then in one instrument you keep preparing state 0. In the other instrument you keep preparing state 1. Okay, for the school of parallel compatibility, these are compatible. Because you just have one measurement, and then you can just prepare 0, tensor 1, and you take the partial trace of the one you like, right? But these are classically incompatible because I can signal. By looking at the output, if the output is 0, I know that I wanted to measure this instrument. If the output is 1, I know I want to measure this instrument. So this is signaling from the program to the output, plus the quantum output. So it is classically incompatible, but this is parallel. So these two examples are so silly, in my opinion, that it's not okay to have two definitions of incompatibility that, you know, are not able to agree on such trivial counterexamples, right? Okay, so now the two problems are presented. What can I do? I still have 15 minutes.
No, you have, yeah,
Okay.
15 to 20 minutes.
Okay.
25.
So, okay, let's say you tell me which one you want to see first, and then, you know, the remaining time I will spend for the sharpness thing or the incompatibility thing.
Both.
Both first.
Okay, so let me start from the incompatibility first, and then I will move back to. Okay. So you want to bridge the two camps, come on, right? You want to bridge the two. So how can you do? So this is our proposal, what we call Q compatibility. We refrain from calling like strong compatibility because then it becomes weak incompatibility and becomes very confusing. So just Q compatibility and we're calling Q incompatibility. So still you have a family of instrument, and you say now the family is Q compatible whenever again there exists a mother instrument, and the mother instrument has its own classical outcome and quantum output, and then you have a conditional probability distribution here that processes the classical output depending on the program, but also now you have a family of post-processing channels that in principle can depend on all pieces of classical information there, such that this holds. So a picture is much more revealing, I guess. So it has this triangle structure, like it was the case in the parallel compatibility, because of course parallel compatibility is a special case. So what it means, so you do the mother here you get the program. The mother first sends a classical signal to the program that computes the output depending on the program and mother's outcome, and then sends back everything to the mother side. And here you can apply some CPD as you like. So you see that, for example, if C is taken to be the tensor copy of all the quantum outputs, and the post-processing channel is taken to be the partial trace, you know, the marginalization, you go back to parallel compatibility. And also you get classical compatibility by forcing this guy to be identical, right? So basically you're able with this notion to put an umbrella on both classical compatibility and parallel compatibility. But not only, because now you don't have any sort of artificial constraint, you know? And these constraints basically were coming only because people were starting from intuition from the POVM case, from the POVM situation. So both constraints were kind of unwarranted in the general quantum case. So now you can really build a resource theory for this class of bipartite channels. Bipartite channels that have a quantum input and a quantum output on one side, and a classical input and a classical output on the other. So programmable instruments, right? Because, for example, if you want a resource theory of classical incompatibility, then what you do? Okay, you want some processing of this bipartite channel that preserves this causal structure, so that classical information can only go from Alice to Bob only. So what do you do? Okay, so you imagine a super process or a quantum comp, most of sometimes objects are called, where classical information only goes from Alice to Bob once, before what you have is applied. So if information goes here, and this is also classically compatible, information goes here, you can write everything in the big bulk of this code. So this will keep classically compatible instrument classically compatible, and everything which is not classically compatible is the resource. And you can do the same also for quantum incompatibility. So this Q incompatibility has this V-shaped communication structure. And then also your process, your super map, your super channel will keep this V-shaped classical communication. And it has to be timed in a good way in order to work, right? I mean, what you don't want is that 2 rounds of communication can be done before this channel. This was quite error. Because then Alice would know also the program before applying the instrument, and so she could do any instrument. So you have to time things, but you can even imagine like an experiment, like a bell experiment, where you force the causal structure of classical communication to follow a certain path by timing the questions, a quantum question that you give to Alice and the classical question that you give to Bob. So you can not send them simultaneously, but you carefully time them, and they cannot cheat. Like if they break an inequality, then it means that here they had something that was incompatible to start with. So now that you have also these structures, so basically, what was necessary here? It was necessary just to essentially stop arguing about which was the right definition and try to instead find the structure of these transformations, and now you can construct a resource theory. A resource theory in particular, where you can, for example, discuss sentences like this one, like pre-order, right? So I give you 2 instruments, and then I ask you, is this more incompatible than the other one? Okay. Now you can ask this question in a meaningful way, and you can say, okay, there will be some particular situation where this is better than this one, or more incompatible than this one, or vice versa. But in general, it would be a pre-order, right? So typically, I give you 2 instruments, they are not going to be ordered in any way. But when they are, then it means that this guy can be transformed into the other guy by means of a free operation. So if you're looking at the resource theory of classical incompatibility, for example, your free operation will be these things. If you're looking at the resource theory of Q incompatibility, things will be like this. I'm skipping the resource theory of parallel incompatibility because that is the resource theory of broadcastability. And broadcasting has little to do with incompatibility. You can, for example, you can imagine as a counterexample, for example, a theory in which you only have one measurement, an informationally complete measurement, and all post-processing of this measurement. So measurements are all compatible, but one of them is informationally complete. Okay, so this theory would have measurements that are only compatible, but it would have states that cannot be broadcasted. You cannot broadcast states. Because if you can make 2 copies of a state, you have an information complete measurement that can still represent multiple copies. So, in my opinion, parallel compatibility mixes 2 problems that are in completely different ballparks. On one side, the problem of compatibility, which is related with the idea of extracting information without causing disturbance. On the other side, you have the problem of broadcasting, which is different. Okay, in quantum theory, they are related, but they're not logically related everywhere. There could be some generalized theories in which the 2 problems are separated. Okay, so yeah, so I guess that I can go back to the sharpness now. And yeah, part of you already heard about the sharpness yesterday in a private discussion we had, so that's why I did the incompatibility first. So the definition of sharpness in terms of projections, as we said, seems that it doesn't play well with transformations that you can do. Okay, quantum pre-processing will not work, classical post-processing will not work, and convex mixture. First, you have to tell me what is the dual field again. So you're kind of stuck in a circle there. So what we propose then again is to change the definition of sharp theorems. So we introduce this sharp, not to make confusion. Now sharp has nothing to do with the operators here. It has to do only with the range of the POVM. So what is the range of the POVM? The range of the POVM is the set of probability distributions that you can obtain from given POVM by changing rho in the set of states of your theory. And I say theory because, as you see here, I'm just working with probability distribution. So this is kind of ready to be applied to GPTs, for example, right? It doesn't matter much the form of these operators, dotted matrices or linear operators on a Hilbert space. What matters is that the POVM is a linear map from the convex body of states to a convex body of probability distribution. And now you say that your POVM is sharp whenever its range coincides with the entire probability simplex on X, which is sharp again, because simplexes are also pointed. If you touch them, you hurt yourself. And then, of course, it is dull. Now, you know, the guess is easy. It is dull whenever the range is just a simplex. Okay, so it means that your POVM is dull. All its elements are essentially proportional to the identity. So they don't care about what state you stick into them. They just sample a random variable according to the same probability distribution. And now, with this definition, if you're happy with this definition, you can work out a lot of equivalent characterizations of sharp POVMs. So, for example, POVM is sharp if and only if all operators here have 1, the real number 1 in their spectrum. So, if and only if there exists vector psi x such that is called for all x. And because the POVM has to sum up to identity, automatically you have this, right? Because, yeah, I mean, the sum, if you take the sum of x, they cannot have eigenvalues larger than 1. So if this was 1 already before for some x, it must be 0 for the other vectors, right? So for example, this is sharp. Okay. Even though it's not projector, it has 1 and a 1. And indeed, we were able to go to a projective 1. But you will see that is a pattern. It's not just an accident. Then sharp implies as a necessary condition that the dimension of the hyperspace is never smaller than the number of outcomes because you want this, right? So you cannot have more than d of such objects, right? So in a sense, you can say that non-degenerate observables, so rank 1 projective POVMs are canonical. So you can say these are the minimum. Sharp POVM of smallest dimension given an outcome set. And then also, you know, you remember that sharp POVMs were considered nice, or at least, you know, they appear in von Neumann's foundational books because they allow a repeatable, they have a repeatable instrument that measures them. And in fact, if you just exclude POVMs with 0 elements, just, you know, this can be repeatable, yes, but because there are some outcomes that are repeatable because just they never happen. So it is excluding this thing, which is always dealing with 0 operators is not nice, but anyway. Then the condition that there exists a repeatable instrument, measures POVM, is equivalent to sharp. So if this is what you want, again, you have no reason to think of projective POVM. You should instead think about sharp POVMs because now it's really the thing. And then the dual POVM.
For example, like which whether repeatable or not projector.
Oh, a measurement is repeatable but not a projection. This is different. Why? I can measure those POVMs and then I can prepare these states. So I can do a measure and prepare strategy, for example. I measure the POVM PX, and then depending on the outcome, I prepare these pure states that I know will give you with probability 1 all the times the same outcome. So this POVM admits a repeatable instrument, though it's not though it's not projection.
Is it actually repeatable? I mean, if I apply it twice, there are states for which it is not really repeatable, right?
Yeah, wait. So repeatability is for instruments. Okay. So repeatability for a POVM is a kind of mutuated concept, because I said that the POVM is repeatable if among all instruments that correspond to the POVM, and you have uncountably many, okay, there exists at least one which is repeatable.
Okay.
So I think that here you are thinking of the square root instrument. If you use the square root instrument here, it wouldn't be repeatable. Right? But there is one that is repeatable, and a simple construction would be to say, okay, I measure px, and then depending on the outcome, I prepare the state. And then I keep getting all this. Okay, so now, somehow not only things seems to get together nicely with if and only if and equivalence conditions and stuff, but also now you have that transformations that were illegal before become legal. Because now quantum preprocessing is legal. Why? Because quantum preprocessing you apply IDAGA. I can tell you very quickly. So IDAGA has the property of being spectrum width decreasing. So if you plug a self-adjoint operator into an IDAGA, a channel that is IDAGA, actually just need to be, I guess, positive and unital. It will shrink the spectrum. So because sharpness was defined from having a 1 and at least a 0 in the spectrum, so that the spectrum of this object has to be maximal. Have 0 on one side and have 1 on the other side. The spectrum can only shrink. So if you're lucky, you will end up with another sharp POVM, but typically you will end with something that is not sharp anymore. So now quantum preprocessing are legal operations. And now you have the concept of the dual POVM, so you also have convex mixture, right? And then this is one possibility for a complete class of sharpness non-increasing transformation. I'm not saying that this is the class of sharpness non-increasing transformation, because also like in other resource theories, you can have various paradigms that still work fine for your resource. This is the simplest one we could come up with. So you start with, so this is your starting resource. What you do is that you flip a biased coin. If the result is head, you apply some quantum preprocessing on your POVM. If the result is tail, you will just discard the input and you will just randomize out here. And in these are represented as affine maps. This is not a linear map. If you look at this transformation as a transformation of the POVM elements, this is not linear, no, because you can send a 0 element into something that is non-zero. It's an affine transformation. But by extending the picture, somehow you can make you can look upon this class of transformation as linear transformations of extended objects. And again, we are going to have now a programmable POVM here. A programmable POVM where the first program corresponds to the POVM you started from, and then the other ones are the trivial POVMs that output a fixed outcome with probability 1. Okay, so essentially what it means that this is an object where you can choose to measure P, whatever that is, your POVM P, or you can choose to deterministically decide, without looking at anything, you can decide any outcome you like. Okay? This is the notion of this program. And now it is very simple to see that the affine transformations that I showed you before can be seen as a local preprocessing of these bipartite blocks, where you have something that processes the program, something that processes the quantum input, and then you might have, if you want, some shared classical random variable R. So in a sense, we go back again to local operation and shared randomness, which is a class of transformations that have accompanied my career since long ago. LOSR. Okay, so and then you know you can have this sharpness preorder and say I give you two POVMs and you say that P is sharper than Q whenever there exists a classifying operation going from P into Q. Okay? Or equivalently, if there exists a CPTP linear map E such that Q belongs to the convex half of this. So here you have your transform P, and here you have this trivial deterministic POVMs. And then you have maximal and minimal elements. So you can say that what we defined before to be sharp happens to coincide with elements that are maximal for this defined operation order. Maximal defined in this way that if you have any other POVM that is sharper than P, then P also has to be sharper than P. So it means that there is nothing that is strictly sharper than P. These are the maximal elements, and these are exactly sharp POVMs defined with respect to the range, okay, the simplex of our distribution. And dull POVMs that are minimal in the sense that there is nothing that is strictly below them. If you have a POVM that can be obtained from P with a falsifying operation, also the vice versa is true. So you have really a kind of double diamond, a kind of cone structure to this resource theory, where on top you have all sharp POVM because they're all equivalent, right? You can move from one to another equivalently with falsifying operation, and at the bottom you have all dull POVM, which again are all equivalent. And in the middle, you have a complicated structure like a poset. It's called anyway, like the structure that you get when you have the order.
Is it the dull POVM, sharp POVM just the identity and kind of partitions of it with
Yeah.
probability?
So first of all, this tells you that any dull POVM is equivalent to a sharp. So you can just give me one dull POVM and that's enough. And one dull POVM could be, for example, identity 0, 0, 0, 0, 0, 0, or for example, identity divided n, identity divided n, identity divided n,
Okay.
a fair dice.
Okay.
These are all free here by construction.
Okay.
Okay. So then once you reach this point, then boom, like essentially the theory is done. What you're left to do is to find a complete set of monotones. So functions that are non-increasing under the action of sharpness non-increasing operations. And they are all of this form, typically. Well, there are many. Okay, you can come up with many of them. The class of monotones that we consider have this form. Where you do essentially what do you take your so these are defined by a uniform ensemble of states. So there's always a uniform probability distribution. These are states, okay, and then your function, say that this is ensemble E. Oh no, E was a chunk. So say this is family F of states, and then you can use this to compute some real number out of your POVM by taking the maximum over this classifying. Is it correct? There are two ones.
You falsified the spelling.
Yeah.
Okay.
And then we will have so you're free to do anything. So by varying this guy here, you change the game. And the game is to say, okay, I start from a given POVM, and I can do any classifying operation on it. And I want to maximize this guessing probability. Okay, so then if you have two POBMs and if you have two POBMs and one of them always gives you a payoff function that is better than the other for all such games, then you know that there exists a classifying operation for one to the other. Yeah, so I think this is all what I wanted to tell you today, and I thank you for your attention.
Any more questions? Go ahead.
I have several questions. So the first one, this example you gave for the quantum pre-processing, no?
Yes.
Okay, so your initial POVM was acting on a qubit,
Yes.
and the final one acts on a qubit, and
Yeah.
somehow it seems to me like you're restricting the possible input states to the original POVM that was a qubit, no? I mean, is it illegal what? Because the map was defined from a qubit into a qubit, no?
Yes, and so the other one goes the other way.
Yes, this I understand, but somehow I would say that you would need to define the pre-processing on the qubit, because actually the POVM acts on a qubit. And you
was-
expect
yes.
it.
Yeah, so, yeah, I think, so the idea is that you have, okay, your POVM P,
Yes.
okay? So this acts on something, say C, D, O,
Yeah.
system 8, okay? So you take system 8, so what does it mean that you do it, you do a quantum pre-processing here? It means that here you take some channel P from B to A, okay? So looking from this side, so here you plug states.
Yeah, I understand.
So this is a CPTP map from B to A, but because you want this to hold for all states flow, then what it is, this is equal to the POVM.
Yeah, I understand the math, but somehow.
Right.
Yes, I understand this, but. Like the first POVM can act on a qubit, no? And
Yes, so this is the qubit, right?
yeah, but not B anymore, no?
In this case, no, but my goal was just to show that there was a channel.
No, but I know what you're saying.
I understand the math,
funny
but-
thing is that he gives preference to the number of outcomes and not to the inputs.
Yes.
Yes.
Okay.
Yes. For sharpness and
Somehow-
somehow the number of outcomes is to be.
I mean, I understand the math, of course, I mean, it's a new POVM, but now it's on a qubit. Yeah, and then also, I had two more questions. Okay, so then there was this parallel compatibility that was
Yeah.
margin, when you take marginals, right?
Yep.
Yes. And now you define the Q compatibility.
Yeah, the Q compatibility here you have just a C,
Yes,
a completely generic system C,
but
and
then
here you
quantum
have.
processing is arbitrary, no? Now-
It's not only.
Yeah, okay. I must say, when I saw this, I thought that it was a bit stupid to take marginal. I think it was very.
Don't tell these other people. Don't tell them.
And
No, I mean, it is natural because they want to say, you know, what does it mean to be compatible? It means that you want to be able also to distribute this thing, but I think it's too much,
like, because I then I felt like, okay, maybe you can encode the operation you want to do depending on I on the B's, but then for that you need to clone.
Yes,
So you see that,
exactly, but
okay, and now last question, like
Yes.
with your new definitions now, all the problems you had with quantum pre-processing and are solved, no? With the-
yes, so basically what you have is that still post-processing
you
can
have to
increase because you really cannot. But there could also be some way to include post-processing, but not this one. For example, this is a post-processing that is irreversible, right? I mean, you're strictly losing information. So it could be that you can, for example, still, for example, if you're processing just a permutation of outcome, that doesn't change sharpness, right? And permutation is reversible, right? On the other hand, also reversible will be splitting this into two. It would be reversible, but it would change sharpness. But there could be maybe a smart way to say, okay, yeah, sharpness also behaves well under this restricted set of post-processing.
Thank you. You had a question, right?
Oh, sure. Yeah, coming back just to the original definition of incompatibility for POVMs.
Yeah.
That they can be pre-processed from the same mother.
Yep.
Or post-processed from the same mother. How does that connect conceptually to just a naive idea of compatibility, or say an uncertainty principle? How can I see that that's the right definition?
Oh, because it means that in a laboratory that only has observable like this, it means that actually there's only one measurement. So that all the other things can essentially be measured simultaneously. It is like an observational entropy, no? Where phenomenon says, okay, what is a macroscopic observer? Macroscopic observer is not an agent, macroscopic observer is a list of physical quantities that can be measured simultaneously. So now we know that being measured simultaneously means there is another. And so the 12th original entropy essentially depends on one POVM. That's your observer. If I give you one POVM, it's a macroscopic observer. All the other ones can be.
I guess what I'm really asking is sort of the converse. How can I easily see that if I give you an X and a P measurement, or a sigma X and a sigma Z measurement, that I can't come up with some crazy mother that will let me pre-process both from it?
Well, finding a mother is a semi-definite linear, semi-definite programming. So you can look upon it's a marginal problem, right? So you have the marginals and you want to find some joint stuff, and you can search for it. And you can actually sometimes verify that there exists no positive marginal. In the same way in which
projective measurements, it's equivalent to correlation.
Oh, for projectivity is equivalent. For projectivity is equivalent to commutative, yes. For POVM is a bit more complicated, but still we can verify whether they're compatible or not.
Is there any relationship between the notion of sharpness that you presented and the notion of sharpness that I might have in my head? No. So when I think of sharpness, so for me, rank one POVMs are sharp, and this can be justified, I don't know, by theory, for example. No, if they're in entangled state, if I can assure you that in the other hand I have a pure state no matter what is the outcome, I will call it sharp.
Yeah.
Is there any relation between these things?
Well, there was a relation, for example, that so sharpness here is given for a set of outcomes. So minimal sharp POVM for a set of outcomes are rank one non-degenerate observables. But for example, like so this is rank one. These objects are all rank one, but this would not be sharp. So it has something to do.
Very nice. So what's not sharp about it?
Here you only get something that is at most 1/2. You will never get the full simplex of probability distributions. Here you will be left with something that is right, like you cannot get 1 here and 0 here, because this is exactly the same operator. So you will always be essentially left with
Okay, but in terms of information you extract, it's the same, no?
yeah, well, yes, that's a
I would
different
say-
definition of sharpness. So yeah, I mean, fair enough, they don't coincide.
No, I'm thinking if where I use it, because I use it,
Mhm.
I talk to people,
Mhm.
and I want to see if I can find
I see.
people who misunderstand me.
I see.
Maybe
I don't know, typically,
at
well,
least a zero in respect because it's the one,
Okay.
because there's some ambiguities.
oh, yeah, there could be other ways to do this. Yeah, they all have their,
Of the simplex element.
because if you define sharpness this way, it is really about a kind of communication capacity figure, sort of. So your PVM is sharp if you can have the whole simplex Fourier distribution. And then when this simplex shrinks somehow. So by the way, it's also an interesting problem to characterize the range of a given POVM, right? So I give you a POVM, Px, and the range is a set of probability distributions, P1, Px, such that Px is equal to the trace of some rho with your POVM. Right? So essentially, what is the image of the set of states through some POVM? That is a problem that is closely related, and it's quite interesting.
No questions? So let us thank the speakers and
Thank you. Thank you.
yes, so Francesco will